Welcome back. Our first talk in this afternoon session is Ali Pomoni, who will tell us about some exciting news from N=2 superconformal field theories. Please, Ali.
Alessandro, is it too much?
There's a feedback now.
Yeah, maybe we put it. Is it okay? Yes? Okay. Okay, let's do it. Okay, I begin by thanking the organizers. It's a great pleasure to give a talk here.
If you want, probably you can.
Oh, yes, yes.
Is that right?
So I take off the mask and give COVID to everyone. Yes. Okay, so let's start. This is work, there was a paper last year which was exploring more the direction of whether we have integrability or not for N=2 theories and how we can go about doing that. And my talk today will be mostly based on a paper that whenever I have a week alone at home will come out. And this is more about how to see quantum symmetries appearing for the spin chains of N=2 theories. And okay, honestly, this motivation is not needed in this crowd, but anyway, it's nice to start in a relaxed way. So yeah, N=4 is integrable. People here are working on maybe deformations, a way of that. But my point is, can we honestly start removing symmetry from the gauge theory point of view and see how we can, in a systematic way, keep or not integrability, how, when, and why. And I really want to emphasize the systematic way. And I hope that by the end, you will see the systematic way appearing. And also with the previous talks, there are so many things that are in common. So I think by now, all of these different eta deformations, whatever, we should really come together somehow. Okay, first of all, let me begin about the past. And in some ways, it's an apology about my behavior. So back in the day of my PhD, we computed already there the spin chains for N=2 theories. We checked the Young-Baxter equation, and we saw that it's not satisfied. And we very quickly said, oh, they are not integrable, and we got depressed. And then nobody wanted to work on them anymore, and that was the end of it. But so basically today, I will try to tell you that this was not a smart thing to do. So the fact that the Young-Baxter equation is not satisfied absolutely does not kill integrability. And let's go slowly first to say why. So we all know here in this room that integrable models are classified. First, we have rational models like XXX spin chain. XXX enjoys a fullest U2 symmetry. The moment you go to trigonometric models, for example, XXZ spin chain, we naively have only a U1. But if you look closely and you are careful with how you play with your boundary conditions, you see that, in fact, there is a quantum SU2 group governing the spectrum of this spin chain. And even more crazy, when the model is elliptic, for example, SYZ, there, naively, there is no symmetry at all. But again, if you do the job properly, you, in fact, see that there is a doubly deformed SU2. And in fact, I want to also insist, because this will be very important when you want to construct crazy gauge theories, like of whatever you want, hyperelliptic models will come to play. And we know, we know very little about these things, but we know they appear, for example, for the chiral pots. So there are examples out there. Great. So now let's, because I don't want to go completely crazy, I want to stay at a level that I can actually do things. Let's stick with elliptic models. And let's first make some comments. So usually when you have an elliptic model, it really depends on the basis you use to write down your Hilbert space, on whether you will have a Young-Baxter equation or not. So the most usual thing, in fact, is that you get a modified or dynamical Young-Baxter equation. And this is what Felder did in '94. Of course, there is a representation, the representation of the R matrix from Baxter and Bellavin. which actually does satisfy the usual Young-Baxter equation. But in that basis, there is Kleanin algebra, and this acts on this Hilbert space. And with Kleanin algebra, you can show that there is no highest weight state on that Hilbert space. But this is really what we do not want when we are studying superconformal field theories. When we study superconformal field theories, we have BPS operators, and they correspond to highest weight states. So if you want to describe BPS operators, you really need another algebra, not the Kleanin algebra. So in fact, you really need to go to something like a Felder algebra.
Can I ask you,
Yes.
Is this something that you can always do? For instance, in XYZ, would there be such a basis where you have highest weight state, but you don't obey the classic?
Yes, this is what Felder is doing for you. This is what Felder did, basically.
So that would be the, for instance, the XYZ would fall into that.
This is precisely that, yes. This is precisely Felder's work.
Okay.
Yes? Yes, please.
Just a quick precision. What's the lag? Because
what's the lag?
No, what's the lag? Is that there is no highest weight state and you want one, or
so
is that you cannot do a BA, some kind of?
What is BA?
Bethe-ansatz. There is.
No. Here the problem is not that you cannot do Bethe-ansatz.
That's the
Baxter
point.
solved the problem with his famous XYZ. The problem is that there is no highest weight state. And this, like when you want to have BPS operators, and we know we have, you cannot, like the correspondence breaks, basically. The spin chain operator correspondence breaks.
With generalized ABA, you can get the highest weight state, for example.
But the point is not the Bethe-ansatz. The point is already at the level of the Hilbert space and the algebra.
Yeah, that's what I'm talking about.
So you need to have a creation or annihilation operator that kills the vacuum. And here, the BPS operators are the vacua. Good. And this is all great, but there is even a little bit of a broader mathematical framework which we can actually use to study these models. And in fact, this is how I will go about. There is a framework of quasi-Hopf algebras. And whenever there is I mean, I am not going to go into detail, and I will definitely not explain in a math, but whenever there is a Drinfeld twist, we always can construct a quasi-Hopf algebra, and a quasi-Hopf Young-Baxter equation is obeyed. So this is the most general beast you can actually hope to get, with phi being the co-associator. And if you want this general beast to be an elliptic integrable model, what happens is that there is a cocycle condition. And the moment this cocycle condition is satisfied, this general framework goes down to a dynamical Young-Baxter equation a la Felder. So this is the way I'm thinking. So I will first show you that we have quasi-Hopf algebras. And then, I mean, I'm not going to do this in this talk, but the next step is to check the cocycle condition. This is my way of thinking. Great. So by the way, when Arkady was giving his talk, I already realized that I am horrible, because when you talked about n equal to 2 theories, you cited the old papers from West, but I am already citing the modern, so the classification of n equal to 2 superconformal theories. So anyway, the point of this thing is that n equal to 2 superconformal field theories are classified, the ones with the Lagrangian description, of course. And we know them. There is, you open the paper and there is a complete list. And what you learn when you just open and look at the paper is that most of the n equal to 2 theories that you want to study are in fact obtained by orbifolding n equal to 4 super Young-Mills. And this is really great, and it was already there in Arkady's talk for many reasons. So first of all, we know the gravity duals, and we can actually really play. We also know that at the orbifold point, so when there is no marginal deformation, we go at the center of the conformal manifold. There, we know that these theories are integrable, the way we know and love about integrability. And the only thing we need to learn how to do is we need to understand how to marginally deform them away from the origin of the conformal manifold. That's the only thing we need to understand. Now, again, Arkady had this theory in his slides, but this is my nice way of writing things, the way I, like for more than 10 years now, I am writing things down. So I will study this SUN cross SUN quiver. This quiver is obtained by orbifolding n equal to 4 super Young Mills by a Z2 orbifold. It has two color groups, 1 and 2. And I think that I allow for the two coupling constants to be general and different from each other. When the two coupling constants are equal, we are at the orbifold point where we know the theory is integrable. And the way I like to think of this theory coming as an orbifold of n equal to 4, I think, for example, of the three scalars of n equal to 4 super Young Mills as after orbifolding becoming bifundamental in the case of x and y, and in the case of z remaining in the adjoint representation. Yes? And maybe the only thing that I would like to ask you to remember is that x and y are the ones that are bifundamental, and this guy is in the adjoint. And maybe just the notation, just to clarify, when I write 1, 2, I mean that Q has one index in the one color group and 2 in the second. And when I write 2, 1 is backwards. Yes? So that's the notation. And for the adjoint, one index is enough to clarify. And this model is, in fact, enough to discover all the things that I care to discover and to go away from that to more crazy n equal to 2 theories. It's, in fact, I mean, OK, I shouldn't say trivial, but it's a more tedious group theory exercise. So it is enough to discover something that the spin chains are dynamical, which will be coming in my next few slides. Then it's also enough to see that the model is elliptic. And also, I write this here because everyone asks all the time, how do you get n equal to 2 superconformal QCD in the Veneziano limit? You just take this theory and you send one of the two coupling constants to 0, and you get super QCD. Yes? So what is the plan from now on? So first, I will concentrate only on one loop. I have to say, we have, from the early days, 10 years ago, with Christoph Sieg, we have even a 3-loop paper. But who cares? This is too hard. Let's be concrete. One loop. Can we see integrability in one loop? So I will try to explain to you here why these spin chains are dynamical. And by the way, when I use the word dynamical, because also here is a community of people that have studied all the Bizert papers, so this is not what Bizert calls dynamical. This is what Felder calls dynamical. So this is very different. So first I will do that very quickly. I will not give you the whole thing. This was the topic of the first paper I cited with Kostas. I will, in this talk, more want to concentrate on seeing the quantum symmetries appearing. So I will first try to explain how we can see the quasi-Hopf symmetry algebra coming up. And then the moment we see this coming up, we will write down the R matrix in the so-called quantum plane, or braid limit for some, depends on what is your language that you prefer, and how to read off the Drinfeld twist. And then the moment we have the Drinfeld twist, we just need to understand it. We just need to understand how to use it, to have a nice coproduct with which we can act on things. And then for this talk, I will then just show you how we can actually construct multiplets of the BPS spectrum, that they are actually bigger than what we thought is there just by knowing n equal to 2 superconformal algebra. They will be some multiplets of some type of n equal to 4 quantum. So they will be just like n equal to 4, but they will be somehow made by a crazy coproduct. Yes? So let's go for this. OK, first a little bit of one loop also to appreciate what is going on here. And please just ask questions if like my notation is crazy or, yes, please ask. So first, let's start very simple with the XY sector. And why this is the most simple? Because people here are familiar with ABJM. And in fact, this sector is very similar to sectors in ABJM. It's a little bit more difficult, but still very, very, very similar. So how do we obtain this sector? You can always think that you start from n equal to 4 super Young-Mills spin chains. By the way, when I write this ket, I think that I take an operator, I cut it open, and I draw the open chain. Yes? So this is an open chain always for me. And then what you do is you use what I just had here. You use these fields. And by plugging in these matrices, you can immediately see that you get two possible n equal to 2 states, spin chain states. And the one is a Z2 conjugate with respect to the other. And on the top of that, you can actually, below what I did is that I was drawing the color indices. So fundamental, anti-fundamental, fundamental, anti-fundamental, and group 1, 2, 2, 1, so that it's planar, right? So it has to be planar. And you can see that this is an alternating spin chain. So this, in this sense, is very similar to ABJM. And the only difference of this state with respect to this state is that here I started with a color group index, open color group index of the color group 1, and the second one of the color group 2. And just by planar contractions, the rest of the indices are immediately determined. So in this sense, this simple alternating spin chain is a dynamical spin chain. You only give the initial information and the rest is fixed. In this sense, it's dynamical. And so then, what is the correct way to label this type of states? Well, it's clear. We just use the n equal to 4 language, and we just say what is the first open index of the chain. And then we have specified all of our Hilbert space. Yes? The moment we do that, we can see what is going on very, very quickly, in fact. So these were the old Feynman diagrams that we computed, and we wrote down the Hamiltonian of the spin chain that acts on this basis. But now, using this new dynamical notation, the basis can be written in this form, right? And in this form, whether you pick I is equal to 1 or 2, means that you have this Hamiltonian or this Hamiltonian. And what does this mean? So both of them, they are an XXX Hamiltonian. The only difference is that the overall parameter in the front of the Hamiltonian here is kappa, and here is 1 over kappa. And by the way, with this kappa, I label the ratio of the two Young-Mills coupling constants. Yes? So what do we have? We have an alternating XXX Hamiltonian. And it has to alternate because the spin chain, the Hilbert space, is alternating. That's the most important lesson on this slide. So the way you should think about it, this is a dynamical XXX spin chain. Let's do something harder. And this is where, like, the full glory, yes. Yes, yes.
Why we're looking only at scalars? In equal 4, we know that that covers everything. What happens
So
here?
what I am doing is enough to do everything, because all the fermions then are in the n equal to 1, if you wish, super multiplet of x, y, z, and then I can just follow my indices. It's enough to show you all the new features. Okay, so this is now the one extra step of difficulty, but also beauty. This is the XZ sector. So X becomes bifundamental after the orbifolding, but Z remains in the adjoint representation of the one or the second color group. And when you do that, so here is the n equal to 4 state, you see what happens. Here it almost looks like it's good and that it's going to be alternating. But these ones, when they start repeating, I don't quite alternate. I stay in the same color group. So for the people that know a little bit of statistical mechanics, this is a dilute model. So this is a truly dynamical spin chain, and there is no way out of that. So it's not like the previous nice alternating guy. Of course, here is like before. The moment I know the n equal to 4 mother theory state from which I started, I only need to specify the first open index, and I specified my state. And also note that this from this, they are just Z2 conjugate with respect to each other, as before. This is a feature of the theory. There is this extra Z2 symmetry there. And now again, you compute your Feynman diagrams, and you write everything down, and you go to this beautiful dynamical notation, and you look at the Hamiltonian. And what do you see? This, the people that have worked on XXZ, they know this is the temporally Lieb Hamiltonian. And the only difference from this matrix and this matrix is that kappa goes to 1 over kappa, like before. So what is this? This is dynamical temporally lib chain. That's what this is. I mean precisely this. That all I need to do, I need to specify at one point of my chain the color index, and then everything else is specified. But I need to do that. Yes, so this is where I am going, actually, yes. I mean, okay, I have to say, okay, so here we go to the apology slide. So this is not the talk that I will give today. This was what we did a little bit in this paper. So when I say dynamical, all the way the point is to go to Felder. So instead of just saying that there is a color index 1 and 2, exactly. There is a dynamical parameter inside the R matrix, and every time I cross a bifundamental field, I have to shift it. Now, why this problem? If it was just Felder, by the way, I would have solved the problem, and now we will be done, and we would say n equal to 2 is integrable, and we are all very happy. But there is a slight catch. The slight catch is the following. So we are clear that we need a dynamical parameter, and the dynamical parameter keeps precisely track of the color group, and there is no way out of that. The difficulty here is the adjoint fields, is this XZ sector that I talked about. And why there is a problem with them? When you cross a Z field, you should not shift the dynamical parameters because you stay in the same color. And what does this mean? In the statistical mechanical language of solid models, this is a dilute model. So this is something that is actually harder than Felder. Of course, these things are studied, and we know a lot about them. And in fact, in this paper, we really wrote down, like we explained what the vertex model that describes the SU3 sector of scalars should be. But unfortunately, this is not something that you can open a paper. There are very similar models that have been constructed, but there is not, the model that we want is not written in a paper that we can just copy it. There is a paper where they do a trigonometric model like this, but not the elliptic one that we want. But this is very close to what exists in the literature of statistical mechanics. So this is where this direction is. Are there any questions up to now? Because now we will shift gears. Yes, please.
If you take in account these modifications, then probably this dynamical Young-Baxter equation will take some modifications.
So the dynamical Young-Baxter equation, depending on where you are on the chain,
Yes.
it will be, when you cross this X or Z, it will look like Felder. But when you cross Z, it will not shift. It will be the same. Mm-hmm. That's what happens. In fact, it's really, really like Felder. You just, let's say, add plus the shift when you cross an X. You say minus that when you cross a Y, and you do nothing when you cross a Z. That's how it works.
Can it be interpreted as some other representation of the...
That I don't know. But so good. So now what I want to talk about symmetry. And what I have been doing the last some months of my life, I want to understand representation theory. And my hope is that if I understand representation theory properly, all of these questions will be just answered for me. So let's just try to go all the way to representation theory. Great. Okay, so first of all, the fact that we see quasi-Hopf symmetry in spin chains coming from gauge theories is absolutely not a new thing. And people have studied marginal deformations of n equal to 4 super Young Mills. And I mean, there is an infinity of papers. And the way we will discover this is identically following what people did in the past. In maybe you could say a slightly more complicated way, because you also have to keep the dynamical plus the quasi-Hopf at the same time. But that's OK. So what we do, here is a summary of what we do. First, we look at the F terms, as always when you study supersymmetric theories. And I will try to explain to you that they define a 3D quantum plane. The moment you have your 3D quantum plane, you can immediately, basically, just by looking at it, read off the R matrix in the quantum plane limit. By the way, then you can plug it in this eigenvalue type equation, and you can recover so you are very sure that you are doing the right thing. And then the moment you have this equation, you win, because you can in fact write down the quantum algebra. And not only that, you can also check, and this is very, very nice and very cool, that actually the superpotential of so the Lagrangian is invariant under this quantum group. So let's do it. First, I start with a baby discussion for what is a quantum plane, the most standard example from Manin. So we just have x and y2 coordinates, and they don't quite commute because of this Q that is there. You open a book of quantum groups, you copy this R matrix, you plug it in this equation, and you get this back, and you are very happy, right? That's how we do it. And then you say, OK, now I want to understand the transformations that leave this quantum plane invariant. And you write something like this. These are the transformations. And these are the things that will actually define for you your SU2 quantum algebra. And what you do to write down the algebra is you just take this R matrix and you plug it in the RTT. And this just gives for you the answer. That's how we do it. There's nothing to think about. Just calculate. Great. But we need three-dimensional quantum planes. And these are thankfully classified by mathematicians. So we just need to understand the math paper. And I don't give here details, but all you need to know, the mathematicians told you, is two tensors with three indices. And once you know these two tensors, this is how your quantum plane looks like, and this is how your quantum coplane looks like. And by the way, for us, because we just do supersymmetric quantum field theories, the quantum coplane is just complex conjugate the quantum plane. That's what it is. So it's very simple. And the moment you have these two tensors, you are very happy, because you can immediately write down your R matrix by using this formula. That's how it works. And this is a theorem. And the moment you have this R matrix, you can plug in the RTT, and you get the quantum SU3 algebra that leaves this quantum plane invariant. That's how you do it. Now, this was done very successfully for the Lee-Strasser, the marginal deformations of n equal to 4 super Young Mills. And many people in this audience know this very, very well. So here is the quantum plane that is obtained by looking at the F terms. So these are the F term conditions. And equivalently, and maybe very cute and fast, is that you can think that instead of writing the n equal to 4 superpotential, which has the epsilon tensor here, you basically just have a more complicated tensor, which you can read off from the Lagrangian that you have. And that's all there is. You just need to know this tensor, and when you complex conjugate, you just complex conjugate basically the epsilon. And by having these two guys, you can immediately write down the R matrix, also the Hamiltonian obeys this equation, and you can prove to yourself that there is a full quantum SU3. So naively, when people started studying Lee-Strasser, they thought that there is only U1 to the third. No, there is a full SU3 quantum there. So we do the same thing. No. Before we do the same thing, I want to say how we should understand this from the ADS-CFT point of view. So what is the gravity dual of this quantum plane? So the moment you have a B field, we just read Seiberg and Witten. So what we do is we have open strings that in the presence of B field, when they end on the D3 branes, they see a non-commutative geometry. Basically, that's it. So the non-commutative geometry is the quantum plane. The open strings see a quantum plane. So our matrices see a quantum plane. That's what it is. And for the Lee-Strasser, this was worked out by Manuela like super many years ago when I was actually a PhD student at Stony Brook. And this is the dictionary between the couplings and the B field. You can copy it from our paper, again, from my PhD days. So the same thing is going to happen. There will be a quantum plane because of this B field. Now let's just do it. So first of all, because we have an orbifold, we have twice as many F-term relations as the ones that we would have for n equal to 4. And not only they are twice as many, so this is, let's say, the one set, and this is the orbifold image of that. they are also sprinkled with this kappa, this ratio between the two coupling constants. And that's why they are quantum. So this here, this cancels, and this is sort of a classical plane, but this is really quantum. And again, you can do the same trick. You can say, oh, I replace the epsilon of n equal to 4 super Young Mills by the tensor that I'm looking for. And you can read it off from the Lagrangian, no problem. And the moment you do that, you immediately plug in this relation that the mathematicians told you, and you get the R matrix. And maybe note one thing, and by the way, in my notation, this is the one part of the Lagrangian, and this is the mirror image of the other under Z2. So this part that corresponds to this epsilon tensor is Z2 conjugate with this part that comes from here, and Z2 conjugate means you send kappa to 1 over kappa. That's what it means. So this is the symmetry of the theory. And let's elaborate a little bit. So just by what we wrote here, or just by looking at the R matrix, you see that for the XY sector, which was the easy alternating sector, the R matrix comes out to be proportional to the identity. And what does this mean? This means that this is a rational model with a full SU2. But we know that this is the SU2 R symmetry of n equal to 2 superconformal algebra. So this is good. Nice. Here, for the XZ sector, the more complicated dilute model, this SU2 R symmetry is now broken. At least naively, we say that it's broken. But what we say here, and this is like the whole, the poem that we say all of this time, is that this gets upgraded to a quantum group. That's what's going on. And just by having the R matrix and splitting it into two in this precise way, we rid off the Drinfeld twist from this equation. And it's given here. Of course, this form implies a normalization, which we can undo whenever we like. But there is some normalization there, and we have the Drinfeld twist.
Sorry. The fact that you have a different signs for, let's say, beta in the two copies looks like something that can be reabsorbed by a change of basis. So
there is a lot about the basis there. There is a lot about the basis.
okay.
So this is in a very specific choice of basis, which is precisely this basis. Like here or here. And this is the basis that makes sense when you have a superconformal field theory. Why? Because XX type of guys, they are the vacuum. So I want XX to be killed by some sigma plus. And then I want ZZ to be killed by some sigma minus, okay? I want my Felder-like quantum algebra.
Okay.
It is very crucial. So I insist on this basis, yes. It is 8 by 8 because here I write in full glory all the possible color indices. And here I use this dynamical notation where by then further saying that the first open index is 1 or 2, I go to this upper part or to this lower part. Take the microphone because maybe it's good also for the camera.
Yes, so can you identify the symmetry algebra of the 8 times 8, or is there some...
Yes, so that's a very good question. I will say a tiny little bit, and in general I will try to avoid because I will have to go very mathematical. So the first layer answer, if you push me more, I maybe will try to say more, is that on this part, which is this, we have a quantum SU2 with quantum deformation kappa. On this part, we have another quantum SU2 with quantum deformation 1 over kappa. And to which of these, how they combine is dictated by the Hilbert space on which we act. And you can try to push me, but okay, maybe later for more words. So this is where we are. We are at the point that we just have a Drinfeld twist and a quasi-Hopf symmetry algebra. Yes? Now, this is all great, and in some sense, maybe a mathematician would be very happy, but I am a physicist, and I want to see the multiplets. So from now on, the goal is to see the multiplets. I want to see the particles coming together in the bigger than expected multiplets. with my hands. Yes? So the first task, and maybe also many people in this audience are actually, they know these papers very well. So I was actually very much inspired by these papers when I did this, when I started at least doing this. So these are for the beta deformed mostly. So the first thing that I want to do, I want to write my coproduct. So R is the R symmetry generator. Naively, this was there for n equal to 4 super young males. The fact that there is this index and this hatted index, this would mean 1 and 2 of the n equal to 4 are symmetry, and this would mean 3 and 4. So these are the broken generators. So I am looking for a coproduct that is a rewriting of this. It can be obtained by having this twist that can be written in this beautiful form. This is what I'm looking for. And this is very easy. You can just do that. It's a very, like, one-line exercise. Now, the moment you discover that you can actually write something like that, you can first ask, is my Lagrangian invariant under this? And the answer is yes. You can check your, like, the superpotential is the non-trivial part. You can check that the superpotential is invariant under this. And in fact, there is even some ambiguity. You can even write a few different things that allow for this thing to happen. And not only that, then you can start building multiplets by multiplets. First, for example, you can start with SU2 multiplets, that, you know, the broken SU2 that was not supposed to be there, then move to the SU3, and then to the SU4. And eventually, okay, this we do not have yet. We want to have the full supergroup. But this is also like what Arkady asked. Actually, just because of having this, plus n equal to 1 supersymmetry is enough to guarantee this. So in some sense, this will just be a tedious writing out everything. We don't really have to do it. So, yes?
In the ordinary case, this should reduce to some Youngian invariance, right?
So we will not have that now. What we will have now is an elliptic toroidal.
Sure, but if you were to take the limit k equals to 1, let's say.
Yes, then you get the Youngian, and this is precisely the Youngian that the orbifolds enjoy. So
but
k is equal to 1 is the orbifold limit that you know and love.
Because I remember that in that case, there was this work of Niklas and Alexander Karus. It was pretty subtle, I think, right, to check the invariance of the Lagrangian. I mean, they had some papers on that.
Okay, good. So this is as subtle as what they have.
So it's,
maybe
it's
slightly
similar,
harder,
it's similar
but
to that what they did.
It's basically, so
Conceptually.
Garus is the same, the paper for the beta deformed.
Yes.
So it's basically the same level of difficulty.
Okay.
Once you know how to do the one, you can do the other. In our case, the only extra difficulty is we keep track of the color indices a little bit more and the coupling constants. But you can really follow. This is just a calculation.
Could you say again about possible dual interpretation? Because this quiver is definitely is quite complicated on dual side.
I mean, it's complicated,
Its
but
orbifold
also
point is simple.
at
but
a naive level is very easy. So
would you expect the same symmetry somehow built in?
Oh yes, oh yes.
If you knew what's the string dual.
I mean, naively, the string dual is ADS5 cross S5 mod Z2 with the B field, and the B field is maybe I can.
Is that true?
Yes, so this should be true. So this is the B field, sorry. Where is it? So that's the only extra equation you need to know.
Yeah, but then you. I think it's different. It's get back reaction and deform. This is kind of.
I think there cannot be back reaction from this because this is a constant B field. And for example, when you plug in supergravity equations of motion, H, which is what appear, always cancels. So this will do nothing. Yes. So I know that there is a paper by Aharoni and friends, back from the 99 maybe, which say that this is good. Yes. And also I have to say, I haven't done any calculations. I'm just telling what is the dictionary. I mean, honestly, it would be really amazing that we start looking at these things now. This will be part of the outlook. Okay, so this is where we are, and let's just look at multiplets. And for this talk and for the first paper that will come out, I only do BPS multiplets, but now we are also, I will tell you, slowly are working on all type of multiplets. It's just that, you just need to do it, case by case and over again. So here is an example of a broken SU2, so naively not a multiplet, but what happens is that it is a multiplet. So this operator is a sort of a baryonic operator, and this belongs in a specific n equal to 2 representation algebra. And this, for example, is a completely different but also highest weight state of the n equal to 2 superconformal algebra. But now that we have this nice twisted coproduct, we can act with it, and we can create all the intermediate states all the way from here to here, and all the way back up. So this is as consistent of a multiplet as you would ever hope in your life. This is what we learn in quantum mechanics, with just a more horrible coproduct. And what is also really cool, so back in the day when I was doing my PhD, we sat down and we diagonalized the Hamiltonian by brute force just because our PhD advisor told us that we need to do this. And we got this crazy, kappa sprinkled forms for the states. With the coproduct, you can get everything up to all the factors, completely, beautifully everything. So for me, when I got that, that was amazing. So this is how the SU2 multiplet works. And you can do the same thing for SU3 multiplets, but okay, I don't do it because I don't want to have to draw bigger dimensional things, but you can do it the same way we learn SU3 when we learn the 8-fold thingy. So you can draw these beautiful multiplets, as long as you use your coproduct. And then what was actually, this is something that took some time, because then we really need to make sure that we can embed properly SU2 and SU3 inside the SU4. And why this is hard? Because SU2 and SU3, we were only looking at holomorphic operators, but now you really need to look also at non-holomorphic operators, and you need to get all of the reality conditions right. But now we have it. So naively, this is the 20 prime multiplet of n equal to 4 super Young-Mills. And this is a proper multiplet the moment you set the coupling constants to be equal, or if you wish, you don't orbifold even. But now, we want to say that this is a proper multiplet of the full quantum group. First of all, let me just say that this green SU2 is the SU2R symmetry of the n equal to 2 representation theory, and we know that we have it. So moving in this multiplet in these ways is guaranteed from the n equal to 2 supersymmetry. There is nothing to check there. Of course, we check it for notations and for normalizations, but it's guaranteed. The point is the blue. So the blue is done with the broken generators after you upgrade them to quantum with your new coproduct. And the point is that you can really go and do all these steps and build this multiplet completely. And this multiplet, for the people that don't know, this is the stress energy tensor multiplet of n equal to 4 super Young-Mills. So this is the scalar that begins the multiplet of the stress energy tensor. This is the n equal to 2 chiral ring, the Coulomb branch operators. This is these mesons that are on the Higgs branch of n equal to 2 theories. And magically, they are all in one multiplet, a new quantum multiplet. Did I say everything that I wanted? Yes. Now, here is the conjecture. Also, I want to insist, what I did, I really used this very specific theory. But what I did, it was just orbifold and marginally deform. So I will make a very strong conjecture, which I really believe is true, that all theories that you can get from n equal to 4 super Young-Mills with less supersymmetry via orbifolding or orientifolding or whatever, but in this direction, so break our symmetry in a way, from the mother n equal to 4 theories, they are all enjoying a quantum deformation of the n equal to 4 supergroup. This is the conjecture. And all the naively broken generators of the PSU2,2/4, they get upgraded to quantum generators. And there should be a way to do this and do also this. And again, the way you break asymmetry is the way that you just, way you break supersymmetry is the way that you break asymmetry. So you do something to the 5 sphere, and you leave the ADS5 part alone. Okay? No. So when the theory is not supersymmetric, there is a double trace deformations, and these are very bad. Yeah. No, so don't do that. Yes. So supersymmetric, so that we have BPS happiness. Good. So, and here is a summary, like a more visual maybe summary. So n equal to 4 super young mills, when you look at the F terms, they are like classical planes and they have SO6 symmetry. But now we have some cone. So we break this nice SO6 naively. But then by writing down the F terms and looking at them as quantum planes, we discover in precisely this way the quantum, if you wish, SO6, or quantum SU4. And the precisely way I described. First, you write down the R matrix. Then you plug into the RTT. So this is my summary that guarantees that it should work for any, yeah, I'm finishing. Yeah. So then you have your nice quantum group. It's very easy, as I showed you. You just split the R matrix into 2, and you get your Drinfeld twists. Of course, you always have to choose your bases nicely, and you choose your bases according to superconformal representation theory. And then the moment you have your Drinfeld this, you have a guaranteed quasi-Hopf happiness. Okay, so this is a summary, because this talk was only about these multiplets, which I'm very proud of, but there is much more to do. So first of all, I only discussed this Z2 quiver, but by now we can do the full family of A-type orbifolds, so ZK. We can just do the same thing for all of them. And it's basically the same. You just have K copies of the same thing, and it just works the same way. We are now in a process of, going, delta is equal to 2, delta is equal to 3, and just constructing multiplets. For example, we can do 6 times 6, and we have 1 plus 15 plus 20 prime. 20 prime I showed you is a BPS multiplet, but 15 also, we can also do the 15, and it's a non-BPS, and we can just do it. And then, you just continue. I mean, okay, I don't think I will want to do much more than maybe 4 of them, but just continue doing. And in some sense, we are experimentally discovering the representation theory of this quantum group now. In the paper that I cited before with Kostas and Randall, we studied this 15 vertex model. And this is a whole thing that there are a lot of things that need to be done there. So we have a very formal definition for what is this 15 vertex model, but now we really need to solve it. We really need, these are, anyway, we really need to do this. Another thing that we have, which is very nice because you can compare all your results, we have an explicit coordinate Bethe-Ansatz study. And actually, this was the first thing that I did sort of almost, 6, 7 years ago. I was calculating, what happens to, collide. And I found this equation. And I was like, oh, whoa, wait. This was a one loop calculation, but I got this square root that we know from n equal to 4 for all loops. So what is going on? So this is one loop.
Why the sign is minus?
This is how the sign is. Yes, but it's very similar. So if you put whatever, some number of kappa squareds minus the g squared, you get the same.
Kappa is equal to 1.
Yeah. For kappa is equal to 1, we expect these are the orbifolds.
I guess you got the cost, right?
You need to, yeah. Yes,
just the cost.
yes. And okay, there is also some work in progress with Anna and with Marius when we look at this crazy, simpler XY sector and try to construct brute force Q3s, and so this is another approach. Just brute force, can you get it? Good. And then, I really want the answer, right? I really want the answer of, is this integrable, yes or no? And the way I am going, so you do the 6 times 6, then you do this. Then, when you learn, you say, can I compare the two twists? The 6, 6, how it goes to 6, 6, 6. This basically experimentally gives for you the so-called cocycle condition. So the moment I have my cocycle condition, I can ask, is this beast integrable, yes or no? That's the way. So this will formally answer this question. And then everything that we know and love from n equal to 4 should just go through. It's basically really the same. And again, for n equal to 1 theories, there are very similar things. The vertex model changes. It can more generally become 19 vertex. But maybe this is even better because Korepin has... so anyway, maybe this is even better. And these are some... OK, please, Arkady, let's understand the gravity dual. Yes, this would be the... I think at this stage, this is one of the most important things. Yes.
Utilization results in this case for G1 moving to G2, and it's very hard to interpret.
But I have these very old papers, actually with Mitev, back in the days when I was here and my beginning days of Hamburg, where I had this crazy conjecture always that there is this exact effective coupling. So for many things like the Wilson loop, you replace the n equal to 4 coupling with a function. Yes, yes. But now we know this crazy J blah blah. Maybe we can really do this now. Yes. And there are two other very cute ways to go in the problem. The one is the Costello style, which actually I think we know quite a lot. So this should be possible to do. And the other thing, also very recently, Francesco wrote with Matthias the string dual to the free n equal to 2. So now we just need to learn how to do the quantum string dual by putting the n equal to 2 multiplets together in quantum n equal to 4. Yes.
So we still have time, yeah.
Yeah, Ellie, thanks for a nice talk. I'm a little bit familiar with this work by Zubos and his PhD student at the time, Dlamini,
Yes.
about like the beta deformation and the more general marginal
Yes.
deformations. So you expect this whole story to apply in that context or
The whole
not?
story goes through identically. The only extra bit of difficulty is this idea of dynamical.
Mm-hmm.
So when I am writing these matrices, let's really compare. So what they have is really you replace this epsilon by 1 epsilon.
Mm-hmm.
So the only difference now is that you have 1, 2, because this is the Z2 orbifold. And this guy by this guy are related by a Z2 symmetry. So each bit here is identically what was done in that paper, or at least the procedure, not the answer.
Sure.
The answer is different.
But the reason I'm asking is because, their results also cover the beta deformation for imaginary beta, for example.
Yes,
And
yes.
in that case, it's known that the string dual is known, and it's known that that is not classically integrable
So
in
first
in
of
a
all,
standard
I
sense.
want to say that whatever we have said in the past that it's not integrable, we should think a second time, because I think no one in this community ever thought about Felder type things.
No,
I think we
certainly.
really need to be careful about these statements.
Right, but then
So I don't accept any statement of non-integrability by now.
okay, but then
I only accept statements of integrability.
okay, but it's
Yes.
it's been shown that these models admit reductions to particle motion which show chaotic behavior. So
Sure.
it cannot be
if you
classical
can do,
integrability
if you
in the
can
classical
do
sense.
something like that, it might work. Yes, it might work.
There might also be a different way in which integrability is realized in some way, but then do you have any idea how that would
The
be?
only thing that I have to say is that elliptic integrability is a very scary beast. And it's really not something we are used to. So we really need to retrain ourselves very much to be able to see it.
Is there
Okay.
any model where this elliptic integrability would be under control, even a toy model?
I think the most toy model is the XYZ spin chain, and it's already a very scary thing. And there are also all the, like, Pierce and Varnar and all of these crazy guys in the 80s, they have like a production. Yeah.
Yeah, hello. Sorry, I walked in about a couple minutes late, and when I did walk in, you were talking about elliptic solutions of the Yang-Baxter equation.
Yes.
But the rest of your talk, they all seem to be rational R matrices.
They look,
What was the role of the elliptic
Yes.
solution here?
actually, in some way, the elliptic is already here, so this is already the elliptic, but I didn't say.
Really, because the elliptic has like
Yeah.
two
So-
parameters,
Yes. So
not just a Q.
Yes,
There's a
yes.
gnome and there's a.
yes.
It's
So
doubly periodic, etc.
Yes.
It looks very different.
First of all, the reason why this does not look elliptic is that this is, I take the rapidity and I set it to one of the two periods. So, and then, of course, so this is the braid limit of the R matrix.
Okay, yeah.
This is
So,
not
but
the full
you're
R
going
matrix.
to a rational limit somehow.
Exactly.
Okay, so you're fixing the. Okay,
Because
okay.
right now, the only thing that I was trying to do is I wanted to pull out the quantum group out of nothing.
Right.
The moment I understand this, then I want to Baxterize.
Yeah,
and
that's going to
write.
have to be deformed
Yes.
to include the gnome or whatever you want to call it in
Yes,
the
yes.
elliptic. Okay, thank you.
More questions? Yeah.
So when you wrote the coproduct, you said that there was some ambiguity there. Is there any meaning for the ambiguity, and you had any particular reason to choose this one, or
So
is there
yes,
anything fundamental about
yes,
it? Or?
so it looks like there are two classes of coproducts that go.
Yes.
So okay, of course there is always normalization, right? But I don't even think about that. The one coproduct looks like it's natural when you study holomorphic things, because what it basically does is you can actually kill either this guy or this guy and put it to 1. In fact, people do this also when they do XXZ. One way of writing the coproduct is having here a 1 and here having Q to the J3. So this is the one way. Someone said something? No. The other actually is very crazy, and I have to say I don't understand it, because these functions are somehow, they look complicated. Maybe we can look at them together, but it looks highly non-trivial, and I have no idea why this other way is allowed.
Yeah, Ellie, just
Yes.
maybe it might be a bit outside, but I'm just wondering, when you, sort of two questions. When you say you want to consider less supersymmetric setups,
Yes.
like n less than 4, and you say that that's a bit generic set, and of course we could expect some quantum realizations of certain symmetries in these reduced cases. You want to expect something concrete? Was this beyond this, as you
Yes,
Nicholas' prescription?
It is really how I said this. The homework is you always write down your F terms. So for example, if we do an n equal to 1 preserving orbifold,
Yeah.
the most simple is a Z3 one with 3 nodes, right? You will have 3 quantum plane images.
Yeah.
You will basically, so this will define for you 3 different, this model will be, by the way, hyperelliptic already. It will be a torus with 2 holes. So already we need more advanced theta functions, not just the normal, but okay. And I mean, yeah, I can just do the same. I can write down these things, I can write down this, I can write down.
Yeah. I'm probably also asking the context if you can go beyond this two-partite quiver. Like if you go to toric diagrams, which have higher degrees, like
So
dimension 3.
everything that can be written with a toric diagram, or equivalently, I had this in my conjecture somewhere.
And all these colors are samely satisfied?
So as long as you can construct an n equal to 1 theory with the brain tiling of Hanani, I think you win. If you give me a brain tiling, I can give you the vertex model.
Few more questions?
Maybe naive question. So suppose you look at orbifold point with equal couplings. You have twisted sect and twisted sect. Now you deform. Are you looking at all states?
Yes.
So it's not just deformation of twisted sectors.
No,
So you're
all.
claiming integrability in the whole.
And you can see this very clearly here. So a state that has only z's in it is an untwisted state, but a state that has x and y is crazy twisted.
Let me ask.
There is another question.
I saw there are a few. I just wanted to use my prerogative to ask some more.
That's not very nice.
Then I'll give them the floor. Again, about, and we already discussed it, but I'm very thick, about this multiplet splitting. If you can show again the thing.
Yes.
So,
Yeah, this is my favorite picture these days.
so my confusion is the claim that the actual spectrum of the full theory would organize in this way, where basically you have this arrow corresponding to
Yes.
the deformed coproduct?
Yes.
Because the thing that confuses me is I thought that the shift in the energy levels of things that used to be descendants or under the ordinary symmetry before you deform and everything actually get corrected in a very like non-algebraic, non-rational way,
No,
like it involves
so
zetas and so on.
Whoever is in this multiplet has the same energy.
Well, no, when you go down, normally even in the undeformed theory, you increase by one, right?
When you go down, you move in our symmetry space, not by the dilatation of the
Yeah, and
vector.
I guess I'm thinking about delta minus j, so that would be like. right.
So delta stays the same,
Yeah,
and our symmetry changes when you move here.
and you say that it changes by something that is, it's something that is determined by the commutation relation of your Q-deform algebra, right?
Absolutely, yes.
And you're saying that this shift is always the same, like, that something that used to be a descendant
There is
will
no
change.
shift on delta. That's what I'm saying. There is no shift on delta.
And the shift on delta minus j is just something that follows simply by this.
It follows simply by basically here, this
Yeah.
axis.
Yeah, I don't know. I still find this a little bit difficult to reconcile with the fact that even in simpler theory, like beta deform, what used to be a descendant acquires anomalous dimensions that are very complicated to express.
Yeah, we talked about this.
Yeah.
So for the beta deform, first of all, here this is just a calculation and there's no discussion, it's a clear calculation. For the beta deformed, as we discussed, most probably, and because actually also we had a difficulty with this guy, to fix this guy, and we had to do something really careful. We had to change the open chain boundary conditions in order
So
to
it's
get
in the
that.
boundary conditions.
So for the beta deformed, maybe we need to rethink carefully how we choose. And you see, this is clear. So when you write the Lagrangian of xxz, not the Lagrangian, Hamiltonian, and when you write the Hamiltonian of temporally lib, if you use this Hamiltonian, you will never see the quantum as U2, just never. If you use the temporally lib Hamiltonian, you will see the quantum as U2. So the quantum as U2 Hamiltonian, temporally lib, commutes with the quantum as U2. The other one doesn't. So it's very possible that the way you write the open spin chain Hamiltonian for the beta deformed is not a good way, and you need to slightly change your boundary conditions, and then you will win.
Okay.
Of course, you need to change the boundary conditions in a way that it's actually allowed, right? So that when you close, you get the right operators.
Very quick question. So you think, you talked about coordinate beta ansatz at some point, right? You think one can set up the calculation of overlaps of beta states?
This is so much later.
Later, eh?
Yeah, I mean, first we need to do baby beta ansatz.
Hello, thank you for the nice talk. Actually, I was curious about the comment on the final slide about the connection to four-dimensional Chern-Simons theory, because
Yes.
for each Chern-Simons theory, if you take the spectral curve to be a torus, and you study the 2D effective theory, you get the BF theory. So I was wondering whether it's a BF-like theory with the model light dependence. So I was wondering whether you already know, you can already see the relation between your story and that story.
Okay,
already.
I have to say, I don't. If I could do it in 5 minutes, I would have done it. Yes. So I cannot do it in 5 minutes.
Okay.
But what is clear to me is that you should be able to take this paper, or you should be able to take the paper with Yamazaki, Costello, and Witten. There they tell you, you replace the plane by a torus and you win. So it should be basically as simple as that. Of course, whatever difficulty will come up when you really calculate. But
Okay.
this is the spirit.
I see. I see.
And that should really work, actually.
Okay. Okay. Thank you.
Okay, I think that we had already a very large number of questions, very interesting talk. So let's thank Ellie again for the talk and the answer. We now have a coffee break until 4:15. right. So welcome back, everyone, for the last talk of the day. And the speaker is Tim Meyer from Humboldt University, and we keep twisting with non-commutative n=4 super-Young Mills via Drinfeld twist. Please, Tim.
Thank you. So, first of all, let me thank the organizers for giving me the chance to speak here. So, yeah, I will present this work about Drinfeld twisting the n=4 super-Young Mills in a non-commutative way. This is based on work together with my PhD advisor, Stijn van Tongeren. And the plan for my talk today is to first give you a motivation where these Drinfeld twists of n=4 arise from, why we are interested in them. Then I will explain to you the Drinfeld twists and how they affect and twist a given algebra. I will give you some examples of deformations for this n=4 super-Young Mills that fall into this class of Drinfeld twists. Some of these examples will be of non-commutative type, so I will explain to you the construction of non-commutative field theories on these examples. These non-commutative spaces and structures also affect the gauge theory, so I will elaborate also on a construction how we can get gauge invariant actions for these deformations. At the end, I will elaborate on the so-called planar equivalence theorem, which enables us to relate planar Feynman diagrams of the deformed theory to their undeformed counterparts. Okay, so first let's start with the motivation. So for me, the starting point is the ADS-CFT correspondence, which in its most famous example relates the ADS5 crosses 5 string to the n=4 super-Young Mills theory. Both of these theories are integrable, at least in their planar limit, and are relatively well studied in the literature. As Sibylle was already telling you in the, before the lunch, on the string theory side, there are a bunch of integrable deformations that have been studied already. One famous class of these deformations is given by the so-called homogeneous Young-Baxter deformations. They take a classical R matrix that fulfills the classical Young-Baxter equation to deform this ADS5 crosses 5 string. This deformation is realized as a twisting of the underlying symmetry algebra, the PSU2, 2/4. And this twist, of course, corresponds to the R matrix that we have chosen to deform the twist, to deform the string. In principle, I'm interested in finding somehow the CFT dual to these deformed strings here. And the natural attempt to look for such a CFT dual is to twist the underlying symmetry of this n=4 super-Young Mills with the same twist that appears here for these deformed strings. And then we can ask about the properties of the arising deformed version of this n=4 super-Young Mills. Also, how do the observables look like, and whether we have integrability for these theories as well. And at the end, we could hopefully find this deformed n=4 super-Young Mills to be the CFT dual of this string theory. The topic of my talk will be basically this green arrow here, so how to get from the n=4 super-Young Mills to its twisted version via this twist. So, as I told you, for me, these twists are somehow defining the deformation here. But to understand these twists, we first need to look at the Hopf algebra structure that we can define on a given Lie algebra. So we take the universal enveloping algebra and equip this with this canonical coproduct structure, as well as the antipode and the co-unit to obtain the Hopf algebra structure here. A Drinfeld twist is then such a twist here that lives in this tensor product of the universal enveloping algebra with itself. We ask some, this should fulfill some properties like invertibility and expandability and some deformation parameter. And then, so for this twist, we just, for this Drinfeld twist, we just ask the usual co-cycle condition, which is this one. So we just consider this usual class, these usual twists, these usual Drinfeld twists here, fulfilling this co-cycle condition and this normalization condition here as well. Right. So this Drinfeld twist then can be used to define a somehow deformed coproduct, which is this coproduct given here. So we just let this twist acting on a given on the canonical coproduct acting on this inverse twist here. And we now want to have a theory that obeys this twisted Hopf algebra structures with this twisted coproduct instead of the undeformed Hopf algebra structures with this undeformed canonical coproduct. In field theories, however, these symmetry algebras act on fields and on their products. So, for example, when we consider the translation generators, so the algebra of translations, this act as partial derivatives on fields and on their products. So clearly, when we act on this pointwise product with a partial derivative of functions, then this is given by the Leibniz rule. And this can be formalized by using the undeformed coproduct. So we introduce this mu that acts on the tensor product of two functions and is defined to give the pointwise product. And if we now act with an element of the Lie algebra, this big X here, this capital X, on this pointwise product, this is realized as the coproduct of X acting on this tensor product of functions here. Okay, so this somehow means that this product of functions here is compatible with the undeformed Hopf algebra structure. But as I told you before, we want to have structures that are compatible with the twisted Hopf algebra structures instead of the untwisted Hopf algebra structures. So what we need to do is to define a somehow twisted or deformed product of functions so that we have structures that are compatible with this deformed Hopf algebra structure. Okay, so let's do that. The twisted product of functions takes this form. So it's basically just this composition of the pointwise product with this inverse twist here. And if we now look on an element of the Lie algebra that acts on this twisted product of functions, we find that this at the end respects the twisted Hopf algebra structure, since this is acting via the twisted coproduct on this tensor product here. Okay, so this is the structure of the product on functions that we are looking for. Okay, and for simplicity and later use, we just call this the star product and we write F star G. The star product, due to the twist, is now non-commutative anymore, but due to the co-cycle condition of the twist, this is still associative. Okay, so this is the object we need to deal with.
Sorry, just to understand. So this is a rather implicit definition, right? The pointwise product of functions has a very explicit definition by taking the value of a function of a point times the value of a function of a point as a C number, right? And so also the derivative and so on, they can be given very explicit definitions. So are you going also to give us some explicit definition of this product, or is it just going to remain like this?
We will come to that in a moment. I mean, in principle, it will become clear when we look at examples for these twists, because these are relatively well defined, and then we can give explicit definitions of these star products here.
Okay, thanks.
But yeah, up to now, this is just the general mathematical structure behind it. And the next step is then to look at the Lie algebra that we would like to deform. And for n equals 4 super Young-Mills, the underlying symmetry algebra is somehow this PSC2, 2/4. And this is the algebra we would like to deform. Okay, this PSC2, 2/4 has different subsections here. So it consists of conformal symmetries, which are space-time symmetries. But we also have some internal R symmetries here that really are just internal symmetries, and we have supercharges. And in principle, we could consider twists that live in different regions of these three parts here. So, for example, there's a well-known deformation of the n equals 4 super Young-Mills, which is called the gamma I deformation, and this can be obtained via such a twist that purely lives in this asymmetry part here. So, just to explain to you the structure, so we basically have 3 deformation parameters, which are these gamma i's, and we have the Cartan charges of the internal SU4 symmetry, and these are the generators here appearing in this twist, and which is used to deform the algebra. And this twist is then also appearing here, here in this definition of this twist function. Okay, so this then introduces some phase shifts of the interaction terms in n equals 4 super Young-Mills. Okay, that clearly breaks some of the symmetries, but it's still an ordinary usual quantum field theory. So we can just consider this as a quantum field theory and calculate observables here. What we are interested in is twists that actually deform this conformal symmetry, so the space-time symmetry of the theory. And therefore I have two examples of these twists. So the first one is called the canonical twist, and it basically takes translation generators to deform the algebra. In terms of the arising non-commutative structures, this is really the canonical example in the literature. So I will take this as a baby example of what we are really looking in, which is this, what we call the Lorentz deformation, which considers a boost and a commuting rotation in this twist here. And we are interested in this because this commutes with a dilatation operator. So we can hope that we have, or we can at least try to find a calculation of the anomalous dimension, which is still meaningful for such a twist here. Okay, so as I told you already, these lead somehow to so-called non-commutative spaces. But why is that? So therefore, we should look at these generators here in the twist more closely. These are vector fields, and therefore they are already seeing coordinates. And since they are seeing coordinates, we can give such a star commutator between coordinates. And in comparison to the undeformed case, this commutator is non-vanishing anymore. So for the canonical case, this is proportional to this theta mu nu, which is constant, but clearly non-vanishing. Additionally, these generators can act as Lie derivatives on the basis 1 forms. But these Lie derivatives with respect to translation generators here are just vanishing. So this means that the twists don't see basis 1 forms. For the Lorentz deformation, the story is more complicated. So here we have a non-constant commutator, for example, for this star commutator between x1 and x0 and x2. And we also have this non-vanishing Lie derivative with respect to Lorentz generators of these basis 1 forms, which actually means that that the twist sees those basis 1 forms. And since these commutators here are non-vanishing, we call those non-commutative spaces. So it's really, so these are just defined in such a way.
I speak about Lie derivatives. It's defined in the standard way.
Yeah.
E plus bi.
Yeah, the Lie derivative is really just the standard Lie derivative here. And these generators here then really just act as the standard Lie derivatives on all the objects. Okay. So now we have these non-commutative spaces. The question is, of course, how we can now define a deformed version of a given theory on these non-commutative spaces, and especially for this n equals 4 super Young-Mills that we are interested in. And the idea is basically to replace products by star products. And this is because we want to have structures that respect the twisted Hopf algebra structure instead of the usual Hopf algebra structures. And this is always obtained via these star products. So this is the overall idea. And then there have been work for this canonical deformation. For example, there's this review from 2003 from Sabo that elaborates on this canonical deformation and gives a construction for this, also including a construction for obtaining gauge invariant theories in this non-commutative deformation. There have been work also on trying to generalize this approach for the canonical deformation for deformations beyond this, this canonical deformation. For example, by these collaborations. The problem here is that these generalizations, in principle, do not really work out properly in terms of gauge invariance. So for all deformations beyond this canonical one, up to now it is only possible to find gauge invariance perturbatively in the deformation parameter. So especially there's no all-order gauge invariant theory beyond the canonical deformation. Okay, with our work we somehow found a deformation in which we really can find a gauge invariant action. So we are really somehow solving this problem here for at least some deformations. And before I come to that point, how it works for deformations beyond the canonical one, I would like to recap how the construction works for the canonical deformation. Okay, so the canonical deformation has a property. So this star product is non-commutative, but whenever we integrate over the full space, this star product becomes cyclic again, which effectively means that we can forget about exactly one of the star products in such a row. This has some consequences, like propagators in this theory remain undeformed. So the kinetic action of a scalar field, for example, has just this one star product, which we can forget about. So it's clearly the undeformed action here. Interactions are really deformed. Like when we consider the 5 to the 4 interaction here, this has 3 star products. We can forget about at least one of them, either here in the middle or one of these at the border. And then there are still 2 star products left over. So this is really deformed. The deformation for this theory sits in the interactions. Okay, so this is scalar theory, but what is about gauge theory here? And the problem with gauge theory is that the gauge transformations are affected by the twist. And this is because they are local, so they depend on coordinates, and therefore the twist can act on them. The solution is to define somehow star gauge transformation instead of the usual gauge transformations. So we introduced, for example, for a joint scalar field, we introduced this star commutator as the transformation rule. And with this, we then can define a covariant derivative on this scalar field, which here again appears with a gauge field combined with this star commutator here. And the transformation rule for this gauge field is then again given via a star commutator here at the end. Okay, so this with this construction it can be shown that we can just deform a given action by replacing products by star products, and this star gauge transformation actually lead to gauge invariant actions. So there's a little caveat. So we cannot define this gauge group to be SUN. And this is because the determinant is not compatible with the star product structure. So we cannot consistently set the determinant of such a group to be 1. So instead of this, we consider, for example, the UN as the gauge group. Okay. So this is for the canonical case. Now let's go to the Lorentz deformation. As I told you already, this has a non-constant commutator between coordinates, but also...
Sorry, wasn't that a singe before? Or?
Yeah, maybe that's a typo then. So,
okay, never mind.
So here, these, as I told you, the twist basically also sees basis 1 forms here. And this is more involving than the canonical case, because it means that we also need to deform the exterior algebra between forms. So basically, we do the same with a wedge product that we did for the pointwise product between functions. We twist it by this composition with this inverse twist here. And then we just call this the star wedge product between forms. This, due to the non-commutativity of the twist, kills the usual commutation rule between forms. But again, when we integrate over those forms, we recast this commutation rule back. And this is in some sense the equivalent to this cyclicity condition here in this deformation, in this canonical deformation. Okay?
Relation, right?
Sorry, again?
Antisymmetry of the exterior algebra is encapsulated in this algebraic relation that you show.
So yeah, basically
the last line, yeah.
Yeah, so we need to integrate to find this antisymmetry of the forms again.
Yeah, okay, that's an analog. That's what I'm saying, right?
Mm-hmm.
Of the exterior standard algebra.
Yeah, in some sense. So just to give you an example, so for this Lorentz deformation, the star wedge product between these dx1 and dx2 has a term that is proportional to dx1 wedge dx2, like in the undeformed case, but there's also another term that is proportional to dx0 wedge dx3, which would disappear in the undeformed limit. So this basis here in the star product, yes, we can. I mean, we can order this with which introduces some prefactors then that are not true. We can choose a canonical ordering here, and this is basically what we will use in a moment. But first, so this is fine. Okay, we have a deformed exterior algebra somehow, but let's look on gauge transformations. And in principle, we have learned from the canonical case that we need to consider star gauge transformations instead of the usual gauge transformations. So let's do the same. Let's consider an adjoint scalar field and just assign the star commutator as the transformation rule for this scalar field. So then, as the next step, we would like to define some covariant derivative on that. And therefore, we need to look at the transformation rule of partial derivatives of these scalar fields. And here, in the transformation, this partial derivative acts on the star commutator. So basically on star products between functions. But this means that this partial derivative here need to act via the twisted coproduct instead of the usual undeformed coproduct on this tensor products here. Which means that this doesn't reduce to the usual Leibniz rule. So it doesn't give the sum of these two commutators. It gives something more complicated, and especially something that cannot be cancelled by the usual transformation rule of this gauge field that we've seen for the canonical case. So this is a complication, but to be honest, this shouldn't really surprise us because we didn't consider consider here that the twist sees also the basis 1 forms. What we instead need to do is, so yeah, this story here doesn't work out, but what we instead need to consider is we need to formulate everything via forms. And okay, these scalar fields are 0 forms, so it makes sense to stick to this star commutator as the transformation rule. But instead, considering partial derivatives of this scalar field, we consider exterior derivatives. And the reason for that is these always commute with Lie derivatives. And since they commute with Lie derivatives, these exterior derivatives always commute with the star product. Because the twists in the star product act via Lie derivatives on the objects. But since this is the case, it is immediately true that the exterior derivative of a scalar field transforms as the sum of these two star commutators, where the exterior derivative either hit the gauge transformation or the scalar field. And now again we can introduce some gauge field, some gauge 1 form this time, that transformed in this proper way, so that this transformation cancels the unwanted term here, and we can define a covariant exterior derivative. Okay, so this is at least consistent, a consistent gauge transformation for this Lorentz deformation. But it means that we need to formulate everything in terms of form, in terms of forms, because these seem to be the natural objects here under this deformation. Okay, so but before we can look at the deformation of a given action, we first should look on the behavior of forms under this twist and in these non-commutative spaces. And therefore, first let's look at these exterior derivatives. So in a given basis, they are just defined via this partial derivatives of a function times this basis 1 forms. Okay, that's okay, and this is what it is, but this is not really respecting the twisted Hopf algebra structure. Instead, we would like to have a star product here in between those objects. So we just define a star derivative somehow acting on this field such that this really respects the twisted Hopf algebra structure. And then we can use this equality between those expressions to relate this star derivative back to this untwisted partial derivative. And there appears this operator, this F inverse with these two indices, but this is nothing else than just the twist function, the inverse twist function, where the second leg in this twist is just acting on basis 1 forms. And therefore it just rotates the basis 1 forms in each other, which gives this index structure here. Okay. For general 1 forms, we can do the same. So they are just defined in a given basis with these component fields, but without a star product here. So we just define these star component fields in such a way that this is the basis 1 form in a given basis of basis 1 forms. And then again, we can relate those component fields with each other. And again, this twist with these two indices here, with these two vector indices, is appearing that we are already familiar with from the star derivatives here. So these twists with two indices in this Lorentz deformation look like this. In principle, like a boost and a rotation, where now these transformation angles here are operator valued and act as operators on functions or forms. On this twist, we can raise and lower indices just using the usual metric, which just means we are inverting these operators somehow. Okay, we can also find a commutation rule between basis 1 forms and functions. So we basically compare the star product between a basis 1 form and a function, and the other way around. And this gives such an R matrix here. And since we are comparing two different kinds of star products, we get two twists. And for the deformations that we are looking in, this R matrix is then exactly the square of this twist. So we now can move fields over basis 1 forms. But we could define as well also a commutation rule for moving basis 1 forms over basis 1 forms, which would allow us to order these basis 1 forms as well. Okay, so we have this deformed exterior algebra, and with this we can also define something like a deformed epsilon tensor. And this, like in the undeformed case, just collects the coefficients of the star product, of the star wedge product between 4 basis 1 forms with respect to this canonical volume form here. And this canonical volume form is chosen in such a way that it uniquely reduces to the undeformed volume form. Okay, so then we have these coefficients of these with respect to this volume form collected in this epsilon tensor. Okay, so we can also move fields over these basis 1 forms here. When we multiply via a star product a function or a field to the very right here, we can move this over all these 4 basis 1 forms, which introduce 4 of these R matrices. So this one here, and then collecting just the coefficients with respect to the volume form gives this epsilon tensor. On the right hand side, we just have the star product between this volume form and a field. But this volume form is uncharged under Lorentz under Lorentz transformations. And since our twist is made out of Lorentz transformations, this is not seen by the twist. So it commutes with every object. So we can just move a function over this volume form without changing anything. So and this then leads to this equation here, which means that whenever we have 4 such R matrices contracted with this generalized epsilon tensor, this reduces to this starred epsilon tensor. And this is due to the unchargedness of this volume form here.
Is there a top form in this deformed exterior algebra?
A top form. So
You have a 5 form, for example?
so we just have, I mean, so we're just considering field theories in 4 dimensions. So this volume form is the...
Yes, but if you take 5 terms like that...
So this is not... There you get 0 because you always can reduce this to this kind of form here. And then you add something additionally, and you can always permute things so that you uniquely get 0. Because whenever you have 2 basis 1 forms, so dx1 star wedge dx1, for example, next to each other, this is always vanishing. Sorry? Yeah, kind of.
Yeah, for example, cohomological.
Yeah, this, so.
Normally in non-commutative geometry you don't have this feature. You can take, if you deform in non-commutative geometry, normally if you deform the 4-dimensional space, you may have a non-trivial 5 form. So your deformation is such that you don't have 5 form.
So I'm
There exist many deformations, non-commutative spaces. So in your case, there exists a top form, which is a 4 form.
I think so. Okay, so right, we have this relation here. So these R matrices contracted with this epsilon tensor always reduce to the epsilon tensor. We can also use this epsilon tensor to generalize the Hodge dual in a given basis. So the Hodge dual of a basis 1 form, respecting the twisted Hopf algebra structure, is given by this star wedge product between these basis 1 forms instead of the usual wedge product. And also we replace the totally antisymmetric epsilon tensor by this starred version of it. And then this is how the Hodge dual for basis 1 forms look like, but we could also define it for the other forms. Okay, so with this we now basically have all the structure on hand that we need to formulate or to understand the structure of forms on this non-commutative space. So the next step, of course, would be to deform a given action. And therefore, I would like to consider this action here, so a Young-Mills action and this action of a scalar real adjoint field. So this is written in terms of component fields, and since forms are the natural objects of the twist here, we first need to write everything here in terms of forms. So this is the action, how it looks like, and we then have here this gauge 2 form and the exterior covariant derivative given by this. Okay, so since this is now written in terms of the fundamental objects, we can just deform this by replacing every product just by star products and using the appropriate definitions of the Hodge duals in this twisted deformed spaces. And this is what we get. Okay, that looks pretty nice and relatively good, but the question is still, is this really gauge invariant? And to answer this question, we need to recap some of the properties. So just by construction, we know that the fields transform covariantly under the star gauge transformations. And we also know that this exterior algebra is cyclic under integration. But since this is the case, the Hodge duals should also better transform covariantly to give a gauge invariant action. And this is what remains to be checked. And therefore, we need first to calculate the transformation rule of these component fields here, of these start component fields that appear in the gauge form. And to get this transformation rule, so this first term immediately follows from this commutator, but the second term, we first need to move this epsilon over these two basis 1 forms. And by doing this, we introduce these two R matrices here. We just get them. So, okay, this is what it is, and this we can now plug into the definition of the Hodge dual. And the first term immediately reduces to the first term that we want to see, but the second term looks like this tiny little mess. But okay, so we can just go on and move this gauge transformation here over these two basis 1 forms, but this time from left to right. So instead of R matrices, we pick up inverse R matrices, especially those two here. And with this first one, we can just lower and raise indices with these metrics here so that they effectively get inverted. So we just have these 4 inverse R matrices acting on this gauge transformation here. But these upper indices here are contracted to this epsilon star tensor. And therefore, we already know that this every time we have such thing appearing, this reduces to this epsilon star tensor itself with these lower indices. But since this is the case, also the second term reduces to the second term needed in this star commutator here. So at the end, we find that this Hodge dual really transforms covariantly under the star gauge transformation, which means that we find a gauge invariant action with this deformation. So, yeah, and this is due to the unchargedness of the volume form, which ensures this relation here. So this is quite remarkable because now we have a deformation in which we can find a gauge invariant action. So we have a deformation beyond the canonical one. So this is really something that was not possible for any deformation in the literature before. Okay, so this is remarkable, but we can do even better. So in n equals 4, so I mean this is just a bosonic theory. In n equals 4, we also have adjoint fermions. And with those, we can proceed analogously to the vector fields. So we introduce some Grassmann-valued, some kind of half forms, these S and S bar that transform under the spin representation, like this. And with these, we treat these psi alpha, so the usual fermionic fields of n equals 4, as components of these objects psi, and simultaneously for these psi bars here. And these are then defined just as the product of these half forms with these component fields, exactly like for the gauge field with basis 1 forms. This again is not respecting the twisted Hopf algebra structure, so we define these start version of these component fields, such that this respects the twisted Hopf algebra structure. Okay, so we can play the same game like with the vector fields. So we can relate these start fields to the unstart ones by having this inverse twist function. This now has spinor indices here, which means that one of the legs is just acting on these basis half forms here, instead of 1 forms. We can also find such a commutation rule between these fields and these basis 1 forms, including this R matrix with spinor indices. Okay. So with this structure now, we can assign gauge transformations to these fundamental objects here instead of the component fields. And when we do this, we can find a deformed action of n equals 4 super Young Mills. And we proceed in the same way like we did for the example before. We first write everything in terms of these fundamental objects, so in terms of these forms and these fundamental fermionic objects. To obtain the right component action, in the undeformed case, for these fermionic actions here, we need to integrate over the Grassmann valued half forms. But okay, so this is then the undeformed n=4 super Young-Mills in terms of these fundamental objects. And this can be immediately deformed by just replacing products by star products. And we can check explicitly that these terms are all gauge invariant, which again gives us this n=4 super Young-Mills for this deformed space beyond the canonical deformation. So that's kind of nice. So this action here has some properties. So when we, for example, consider this kinetic term of the scalar fields, we can choose a basis for these forms and can work out the component fields here, the component field action. When we do this, we arise at this relatively simple looking term. However, this covariant derivatives here include these twists and star products here, where usually we see commutators. Okay, so since this volume form here is uncharged under the twist, we can again forget about one star product here in this integration. So this then just reduces to the usual d mu phi times d mu phi. And for the term that gives the propagator, we can see that this leads to the fact that propagators do not change as well in this Lorentz deformation here. However, as you can see from these terms here, when we plug them in here, we have these twists and additional star products, which means that interactions are really deformed again, also for this Lorentz deformation. Okay, so since we have deformed interactions, we would need to compute new or deformed Feynman diagrams. But luckily, there's something that is called a planar equivalence theorem, and that is proven in the literature for the canonical deformation by Thomas Filk. This relates the deformed planar diagrams to their undeformed counterparts. And the proof, so here for the phi to the 4, works in the following way. So we take this interaction term and we first separate all these fields in their positions. This we do by integration by introducing this dummy integration here, and then we can keep track of these star products, of the twists in these star products separately. And these indices here at these partial derivatives in this twist keep track of which of these fields these derivatives act on. The next step is then in this proof by Filk to Fourier transform these fields here so that these partial derivatives become just momenta. We also have momentum conservation here, and this is then how this interaction looks like in momentum space. And what changes in comparison to the undeformed case is just this this exponential here, this product of exponentials. So let's take a closer look on that. We can redefine these momenta to be the sum of an ingoing and an outgoing momentum. When we do that, this double product of A and B reduces to the single product, where in this exponent we just have neighboring momenta appearing. And these are appearing in this ordered way because this theta mu nu is antisymmetric. But this can be related to some sort of Feynman rule. So for every external leg for this interaction, we draw these doubled lines where we have one outgoing and one incoming momentum. And for these exponentials here, we draw these arrows pointing from the outgoing to the ingoing momentum for each of these vertices. So these little arrows here always go clockwise. With these, we can now draw planar diagrams like this one. And then we see for these inner propagators here that on both sides of these propagators we have appearing these arrows, but they are pointing in opposite directions, which means they cancel against each other effectively. So that means that we don't have star products between internal propagators. They are just star products between external propagators left, which is remarkable because now it is able to we are able to use the undeformed planar diagrams and multiply these star products on the external momenta afterwards. Okay. In N=4 super Young-Mills, we are more interested in Feynman diagrams directly in position space. But we can do a similar proof also in position space. We first again separate the fields in the vertices from each other, like we did here, but then we directly Wick contract to get to the Feynman diagrams. Then we can use the translation invariance of the propagators to relate the twists from one end of the propagator to the other end. And these lead then to cancellations between all the internal star products. So we are again just left with star products that can be mapped to the external positions. So the proof goes as well in position space for this canonical deformation. In principle, we would like to have something similar as well for the Lorentz deformation. So and here we can follow basically the same steps. So again, we separate the fields in the vertices from each other and Wick contract for getting the Feynman diagrams. But instead of using this translation invariance of the propagators, we use Lorentz invariance of them. Okay, there's a caveat. So for example, when we look at the fermionic propagators, these are not really Lorentz invariant on their own. So when we have this Lorentz transformations acting on this component propagators, this is not vanishing. But as we did all the time, we need to consider the right objects. So which means we should take into account these basis half forms for the fermions here as well. And when we do this, this object here is again Lorentz invariant. The same we can also do for the vector fields as well. But with this together, this Lorentz deformation for the proof of this planar equivalence theorem behaves identical to this proof for the canonical deformation here. So we can really have this proof for this planar equivalence theorem for this Lorentz deformation as well. So we can do Feynman integration. Okay, so I think it's time to recap what we've achieved. So we first constructed a consistent Stargauge symmetry for this Lorentz deformation, so for a deformation beyond the canonical one. And we were also able to construct a Stargauge invariant action for this Lorentz deformation. So for a deformation beyond the canonical one, which was not done before in the literature. We were able to adapt the planar equivalence theorem for Feynman diagrams as well. So, but when we look at the properties that allows us to formulate this gauge invariance for the actions in the Lorentz deformation, this is governed by basically two properties. The first is the invariance of the volume form, and the second one is the cyclicity of forms under integration. But this can be generalized immediately to twists that fulfill these two conditions, where S is here the antipode, and these are the elements appearing in the Sweedler notation of the twist, and of course the unchargedness of the volume form. So a bigger class of examples fulfilling these properties are, all, for example, all deformations that lie in this that lie in the Poincaré algebra and fulfill this equation. So this is remarkable because we do not just have a construction that works for one particular deformation, we have a construction that even works for a class of deformations. So this is a huge step. But of course we would like to obtain the integrable structures that we see in the undeformed n=4 also here in a twisted way in this deformed n=4 And usually in this, so in the undeformed n equals 4 super Young Mills, the first hint for integrable structures is it can be obtained by computing the one loop anomalous dimension of some gauge invariant operators. So yeah, therefore we need to construct gauge invariant operators also in our theory. And so this is something that maybe goes too far for this talk, but just to mention it, the problem with these gauge invariant operators is that the usual trace operators are not gauge invariant anymore. And this is due to the non-commutativity of the star product. Instead, we need to introduce operators with somehow twisted boundary conditions that are actually gauge invariant here. And of these, we would like to compute the anomalous dimension, at least one loop, and we would like to obtain the spin change structure, like a nearest neighbor Hamiltonian and the beta equation and beta ansatz in a somehow twisted way. So this is one of the next steps, but another direction would be, of course, to generalize our construction to deformations beyond this class here. So for example, we could consider deformations that include a dilatation operator as a twist, or as a generator in the twist. The dilatation operator wouldn't leave the volume form uncharged, and therefore the construction would break for this twist. And we would like to understand how we can generalize our construction to work as well for such deformations. Okay. Thanks for the attention.
So, are there any further questions? We already had a few, but.
Thank you. So I'm not sure this is a terribly useful question, but just the S alphas look very much like superspace coordinates. I was just wondering, did you look at what happens if you write do all this in n equals 1 superspace, or and whether there is any?
We didn't look at that, and the reason for therefore is that this formulation via forms is something that is already done in the, partially done in the literature, and therefore we just stick to this formulation and just generalized what we had for the fermionic variables as well. And we didn't look on superfield formalism because these non-commutative structures were, like for Kappa-Minkowski case, were studied for theories that naturally don't have supersymmetry. So that was the first thing to look at.
Just related very quickly, the deformations you are looking at, do you know how much supersymmetry they preserve?
That's a good question, but I would say that this deformation breaks supersymmetry completely. I think so. So when we would include the dilatation operator, then there would be a chance to recast n equals 1 supersymmetry, like the beta deformation also preserves n equals 1 as well for deformations in the R symmetry.
Thanks for the nice talk. I was just a bit confused. This epsilon star tensor, should I think of this as just a tensor of numbers?
So it's basically just collecting some numbers depending on the deformation parameter. So just some e to the I lambda, e to the minus I lambdas, or ones or minus ones, depending on these objects here. So for example, when you have dx0, star wedge dx1, dx2, dx3, then this is clearly 1. But when you have something like dx0, star wedge dx2, star wedge dx0, star wedge dx2, which in the undeformed case would vanish, this picks up some sign of lambda.
Right, okay, so it's not totally anti-symmetric in the usual sense.
Right.
Right, okay, thanks.
I just wanted to follow up on Ben's question, because I guess that what you did is not supersymmetric, but rather than touching the dilatation, you could actually combine these with something in R symmetry space, probably, to restore some supersymmetry, I guess, right?
So you mean just considering an additional twist in the R symmetry to recast supersymmetry?
Yeah, something like that. That should be possible.
Well, thinkable, but I would say, yeah, maybe. So yeah, with this.
Yeah, twisted. Yeah.
Well, everything is there twisted.
Yeah, yeah. Well, but I guess it would make sense probably to twist their symmetry simultaneously, right? Otherwise,
Yeah,
I'm not sure. I'm not sure whether there are any theorems as well for this. I mean, what would be protected and what not. But yeah.
Yeah.
Mm-hmm. Yeah, that too. Yeah, another question?
Yeah, according to these last questions, in order to have supersymmetry, you need the equation of motion, I think, because you need closure of the supersymmetric transformations. Are the equation of motion computed? Or can you compute it or put stars when you need? Because you said you have an action, but what happened with the dynamics of that action?
So, I mean, in principle, you can find some equations of motions as well, and they should pick up some deformations as well, like taking star products in between objects. I mean, what you can do is, so for these deformations here, you can always forget about one star product under integration. So when you do a variation with respect to some variable, you can always forget about the star product with respect to this deformation, and then you just collect all the other terms, and this is giving you the equations of motion.
And integration by part is compatible with the exterior derivative you have?
That's a good question, but I would think so. Yes, that's true.
Perhaps it's not automatic.
What I said.
Maybe with a microphone.
We have to say something how the field behave at infinity.
Yeah, that's true.
And so this was not discussed so far.
Have you tried to look at Young-Mills theory on S3 cross R?
So like S3 on cross R, yes. So we thought about looking on this, but the point there is that we have some. I mean, in the undeformed case, we have conformal symmetry. So this should be equivalent to the Minkowski space here.
Right.
But the point is that when we start breaking this conformal symmetry somehow, with this Lorentz twist.
Well, you can keep R still untouched, right? And then you would still have a scale invariance in this.
But then we would need to compute field theory on this somehow curved space, and this seemed to be heavier than sticking to this deformation here.
Well, S3 is a reasonably simple space, isn't it? No?
So, I mean, then we have to know all Feynman diagrams on S3.
Mm-hmm.
Well, why I'm asking this question, as far as I understood in the planar limit, this deformation is the same as undeformed theory, right?
No, it's not the same. So
no. So then okay. Then the question.
So what we have is I mean, in principle, we can compute the same planar diagrams, but we still need to consider star products acting on the external legs. So this is what really changes.
So what's the effect of this action? Is it just the overall phase for each of these?
So it's some non-local operator acting on the positions at the end.
Non-local operator, so not just a multiplication by base. So what do we get for a spin chain?
This is an open question up to now. So I mean, we would expect. I mean, we hope to find something that is twisted in the same way like the spin chain for the corresponding string is twisted, but we still need to tackle this problem for this field theory. We need to do the computations.
Can you comment what is the relation with non-commutative gauge theory of Seiberg and Witten?
So there is this Seiberg and Witten map, in principle. This somehow relates this star gauge symmetry to the usual gauge symmetry, but so we didn't look on that closely because we first wanted to have this construction here for the star gauge symmetry. So we think that there should be, I mean, there should be a Seiberg-Witten map here as well, but this is clearly non-trivial and just known in, I mean, we could just hope to get the Seiberg-Witten map in some perturbation of the deformation parameter. And therefore, we didn't look in detail on this Seiberg-Witten map here.
What happens with topological terms? So if you take FF dual, since epsilon is changed, so what do you get? Do you still have trivial term, or it becomes non-trivial?
This apparently I don't really know. I mean, so.
And similar question for Chern-Simons. I'm just curious about epsilon.
We haven't looked on something like Chern-Simons. So this is a field theory.
So one last question, maybe.
It's related to this last question. Can you define the F potential? Can you define a curvature using your exterior derivative?
So I mean, this is just the deformation of a quantum field theory. So I apparently don't know the answer.
Okay. And the closure of the transformation, because you have this transformation according to the Lie derivative, and then you deform the gauge transformation in order to be compatible, as far as I understood. And all these transformations generates new brackets, you know, if the closure is guaranteed, ensured.
So yeah, I mean, so that's a good point. But so yeah, in principle, so we have this star gauge symmetry here, and this is what we get at the end. And, yeah. So I mean, potentially, so you can have some more brackets, but we didn't. I mean, we didn't. Well, I don't know. So I think. So the point is, we have this star gauge symmetry here that behaves in some sense similar to the undeformed case, but we have this deformed product between these functions here, and this is what we have here in this game.
Okay, that was a very nice talk and also a very nice discussion. Just before we thank Tim again, there will be an announcement by Stein, so don't run away. But let's now give a big hand to Tim and to all the speakers of the day.
All right, yeah, so just some very quick announcement. I hope you all enjoyed the talks for the first day as much as I did. So in 10 to 15 minutes, we'll start the reception outside. It's just right here outside. There are some people who will bake us Flammkuchen, so you can just go there and order what you like. They have some various options. There's also supposed to be some ice cream at some point, I think. Right, then on Thursday, there's the conference dinner. I'll tell you more about this on Thursday, but there's a couple of things. If you somehow didn't register during the registration for the conference dinner, but you would actually really like to come, you have to talk to us and see if there's space, okay? That's one thing. The other thing is there's the option to go swimming before the conference dinner because we're going to be on the water. If you want to do this, you have to inform Jenny or the conference email of this by tomorrow evening. Otherwise, we can't get you in for free. Right now, the weather report is saying it's going to be 36 degrees, so this might be a good idea. But yeah, it's up to you. So let's thank everyone again for today. And see you outside.